So this is a lovely problem. There we go. So this is a strange new type of a problem. We have seen this problem because I just wanted to make sure my students see examples where we factor, but not for the zero. My students sometimes assume that whenever we factor, we're going for the zero, but that's not exactly the case. And this problem also contains some really interesting factoring techniques. And also, it's a Diophantine equation. A Diophantine equation is one where we're not looking for any solutions for an equation, only integer solutions. And because of that, we can solve, say, a single equation with two unknowns in it. With real numbers, that's not the case, right? For three unknowns, you need three equations. For two unknowns, two equations. But in case of Diophantine equations, if you're only looking for integer solutions, you get away with having less equations than unknowns. So this is an example for all of those things. We're looking for all the integer values of n, so that 3n plus 2 divided by n minus 4 is also an integer. Well, if it's an integer, let's call it k. And we're looking for n so that n and k are both integers. All right. So let's see. We clear the denominator by multiplying both sides by n minus 4. And we get 3n plus 2 equals k times n minus 4. And then we distribute k. And then we reduce one side. Well, we can leave the 2 there because it's not going to. And now for the fun part. So we're going to try to factor this. And if you look at it sort of foil reverse, you can say, well, this kn can be explained by we're multiplying two factors, and there is one k here and one n there. And if you're gonna run with that, then k times what? Well, there's a minus 4k here. So if you put minus 4 here, then that negative 4 will meet k here. And then similarly, to get this negative 3n, we're going to put a negative 3 here. Now let's see what that is. If we multiply this out, then we get what we wanted and some extra. We get kn minus 4k minus 3n plus 12. So, well, our expression was this stuff. This is so this here is less than this because we're missing a 12. So let's add 12 to both sides. And now it's factored. And now we can factor it as k minus 3 times n minus 4. Now, this is where looking for an integer works in our benefit. Two numbers multiply to 14. Well, among real numbers, that can happen infinitely many ways. 3 and 14 over 3, right? You multiply 3 and 14 over 3. Well, you get that 14. 7 times 2, 23 times 14 over 23. Pretty much every non-zero number, you take its reciprocal times 14 and it will work. But among integers, now that's a very finite list, right? Not a lot of ways you can express 14 as a product of two integers. In fact, it's what 1 times 14, 2 times 7, that's it. So let's just be a little bit more careful than that. And let's say we want two integers. K minus 3 is one of them, and n minus 4 is another one, so that their product is 14. Yes, I want n here. So we can do 1 times 14 or 14 times 1. 2 times 7 and 7 times 2, and also negative 1 times negative 14, negative 14 times negative 1, negative 2 times negative 7, and negative 7 times negative 2. But that's it. So we have 8 possibilities, and I think all 8 will give you a different n. How to solve for n? Well, if n minus 4 is 14, then n is 18, right? So we just have to add 4 to these numbers. So we can add 4 to 1, we get 5. 7 plus 4 is 11. 2 plus 4 is 6. Negative 10, we're adding 4, 3, negative 4, and plus 2. Okay. So I totally get why 5 should be good. Because if you look at the expression, well, in case of 5, we divide by 1. The numerator is an integer. And the same thing about 3, right? Because 3 minus 4 is negative 1. But these other numbers are kind of a surprise. And even if you do trial and error and we find them all, what gives us the guarantee that there is not a ninth one? This computation not just finds all these 8 solutions, but rules out all the others. Now let's check a few, because it's interesting that there would be exactly 8 integers in the world that does do that. You can stop the video here. We're just going to check a few. So the expression is 3n plus 2 over n minus 4. If n is 18, 3 times 18 is 54, plus 2 is 56, and 18 minus 4 is 14. Yup, that's a fraction. Clearly, 7 divides both upstairs and downstairs. This is 8 times 7. This is 2 times 7. So we get 4. That's an integer. N equals 5 is no surprise because it's 17 over 1, right? 3 times 5 plus 2 is 17, and the denominator guaranteed already. N equals 11 is more interesting, I guess. 33 plus 2 is 35 over 7. Again, it looks like 7 occurs a lot. What's next? 6. N equals 6. 3 times 6 plus 2 is 20. 6 minus 4 is 2. Yep. Negative 10. Negative 28 divided by negative 14 plus 2. 3. It's not going to be much of a surprise. 11 over negative 1. Negative 4. Negative 4. Oh, this should be 3. See, that's why it's good to check. So negative 4 didn't work. Negative 3 should though. 3 times negative 3 plus 2 is negative 7, but so is negative 3 minus 4. And then 2 is the last one. So 3 times 2 is 6 plus 2 is 8 divided by negative 2. Negative 4. So that's it. There are 8 numbers. These 8, 18, 5, 11, 6, negative 10, 3, negative 3, and 2, for which this expression will happen to be an integer. And also, it's good to check. Thank you for watching.